Good day, everybody. Today, we'll be talking about electrochemistry. In this chapter, we will begin with a review of the principles of redox reactions introduced in Chapter 4, and then we'll explore the applications of these reactions in the area known as electrochemistry. In this section, we'll begin by reviewing the basic concepts of redox reactions, or reactions involving the transfer of electrons between substances. Electrochemistry is the branch of chemistry involving redox reactions, specifically reactions that involve transformation between chemical and electrical energy. First, a redox reaction is the sum of two half reactions. The first is the reduction half. The second is the oxidation half reaction. In the reduction half reaction, a reactant will gain electrons and the oxidation state will decrease. In the oxidation half reaction, the reactant loses electrons and the oxidation state will increase. The reduction and oxidation half reactions will always happen simultaneously, and the number of electrons gained during the reduction must exactly match the number of lost during oxidation. Consider the reaction between zinc and the copper 2 ion. That's zinc and the copper 2 ion in the solution. When a zinc metal strip is placed into the solution containing copper 2 ions, so that's the zinc strip, it's placed into the copper 2 solution. We could write these as half reactions. The first half reaction and the second half reactions. This process occurs spontaneously at the surface of the zinc metal strip. As the reaction proceeds, the concentration of the copper 2 ions in the solution decreases and the characteristic blue color decreases, because we do know copper 2 ion carries the blue color. The formation of copper on the surface of the zinc metal is obvious by the black solid precipitate. The reaction is balanced because the number of electrons lost by zinc equals the number of electrons gained by copper. Both are 2 electrons, as you can see in this process. In the previous section, we examined a redox reaction in which the electrons were exchanged directly between the zinc metal and the copper 2 ions in the solution. But what if we could separate these two processes so that the direct exchange of electrons are not feasible? An electrochemical cell is a device that separates the half reactions into separate cells, so the electrons have to flow in an external circuit in order for the reaction to proceed. An example of an electrochemical cell using spontaneous zinc and copper redox reaction discussed previously is presented in this figure here. The oxidation half cell is on the left side, and the oxidation half cell is called the anode. So that's the oxidation half cell, because the oxidation state increases from 0 to +2. That's the oxidation state 0. This is +2 over here. Okay, so I have a mnemonics that can help you remember. So anode is oxidation, because we can use NOx. Oxidation is anode. All right. And the reduction half cell is listed on the right side because the oxidation state changes from +2 to 0. If you still have problems about assigning correct oxidation state, please look at the detailed review in the problem set. For the reduction half cell, we call this half cell cathode. We can remember this by reduction is cathode. So red cat and NOx, because we cannot do NCAT, so it must be NOx and the red cat. In this situation, because the copper 2 ion is not in direct contact with the zinc surface, the electrons cannot be exchanged directly. They must flow from the anode. Look at the electrons always flow out of anode. So electrons will always flow out of anode to the cathode. Okay, so here's where the electron flow. It flows out of the anode to the cathode in the wire. When the electrons flow in the wire to the cathode, they can be used to reduce this copper 2 ion into metal copper. At the same time, please note the cations in the salt bridge will move to the cathode. So Na plus will move to the right side, which is the cathode half cell. And sulfate, which is the anion, will move to the anode half cell. So sulfate will move to the anode half cell. This is extremely important for you to understand how the electrochemical cell works. To remember, cations in the salt bridge will always flow into the cathode half cell, while the anions will flow into the anode half cell. The electrons will flow out of anode to the cathode in the wire, not in the cell. To summarize our discussion so far, an electrochemical cell is a device that converts chemical energy into electrical work. It's also called a battery or a voltaic cell, or electric work into chemical energy. This will be called electrolytic cell. A voltaic cell takes advantage of a spontaneous chemical redox reaction to provide electrical energy, and the batteries are examples of a voltaic cell. A cell diagram, or sometimes it's also called cell notation, is a symbolic representation that provides information about the components of the electrochemical cell and how they are connected. The electrochemical cell consists of two half cells in which the oxidation and reduction half reactions occur. Each half cell contains an electrode, which provides a surface for the transfer of electrons between the species involved in the half reaction. The anode is the electrode at which oxidation occurs. By convention, it's indicated by a negative sign in the voltaic cell and a positive sign in the electrolytic cell. The cathode is the electrode at which the reduction occurs. It is indicated by a positive sign in the voltaic cell and with a negative sign in the electrolytic cell. As you might have noticed, the plus or minus is indicated differently in the electrolytic cell and the voltaic cell. However, the anode is always where the oxidation occurs, and cathode is always the electrode at which the reduction occurs. So you can remember this by NOx. Anode is oxidation, and the red cat, reduction, is where the cathode is. The salt bridge provides physical contact between the two half cells. It connects the two electrolyte solutions, maintains a closed circuit, and eliminates accumulation of charge in either compartment by allowing for ions to flow back and forth. For example, the spontaneous flow of electrons to the cathode would normally result in the accumulation of negative charge in the cathodic half cell. However, the cations can flow from the salt bridge into the cathode. So in this way, the charges are balanced. So the salt bridge not only maintains a closed circuit, it also balanced the charges and prevent the accumulation of charges. In this chapter, we will discuss two different types of electrochemical cells. First, a voltaic cell or a battery. It takes advantage of a spontaneous redox reaction to generate electricity that can be used to power devices like light bulbs, etc. In a voltaic cell, electrons flow from the anode to the cathode because the electrons originate at the anode. The anode is given a negative sign for negatively charged electrons, and the cathode is indicated by the positive sign. In an electrolytic cell, we use an external power source to provide electrical energy to drive a non-spontaneous reaction to the right direction. In this case, the electrons are supplied to the cathode from the external power supply, so the cathode has a negative sign and the anode has the positive sign. But when you compare the voltaic cell and the electrolytic cell, you always see the same flow of the cations and the electrons. You always see the cations in the salt bridge flow into the cathode half cell and anions into the anode half cell. And the electrons will always flow out of the anode to the cathode in the wire. As you can see, that's the anode. Here's the anode. The difference is the assignment of the plus or minus. In the voltaic cell, the plus is assigned to the cathode and negative is assigned to the anode. However, in the electrolytic cell, the plus is assigned to the anode and minus is assigned to cathode, which is opposite to what we see in the voltaic cell. So in the previous examples, we provided illustrations to show the various components of the electrochemical cell. The same information can be presented in a more compact way, which is called a cell diagram or cell notation. The rules for writing the cell diagram are summarized here. You always write the chemical symbol for the anode on the far left and the cathode on the far right. As you can see, that's the anode, that's the cathode. So the double vertical line between them is used to represent the salt bridge. The double line is used to represent the salt bridge. And second, working inward from the electrodes toward the bridge, add symbols to represent the species that are involved in the respective anode and cathode half reactions, using single vertical lines to indicate the phase changes or phase boundaries between the species. For example, you have a solid and then you have a liquid or aqueous phase. Then you will use one line to separate them. You have a solid and aqueous solution. Aqueous and the solid, so that's phase boundary, a vertical line. Okay. And step 3, if known, indicate the concentrations of the dissolved species or the partial pressures of the gases involved in the half cell reactions. For example, you can write the concentrations in the parentheses. If there is no concentration, you can simply write something like this. For example, if you don't have the specific concentration, you can simply write AQ, as you see over here. Okay? So let's summarize this. The double vertical line indicates the salt bridge, and the single vertical line indicates the phase boundary. And you can use aqueous, AQ, in the parentheses to indicate the solution. You can also indicate the specific concentration in the parentheses. So consider the redox reaction in a schematic electrochemical cell shown in this figure. First, copper is the anode and is written on the extreme left in the cell notation. And the silver is the cathode and is written on the extreme right. How do we know if one is anode, the other is the cathode? Because we can look at the reaction and assign the oxidation state. That's a 0, that's a +1, that's +2. By the way, this is called oxidation state we are assigning over here. So oxidation state is increased for copper. So for this reason, this process is called oxidation. Remember, oxidation occurs at the anode. Okay, remember, NOx. Okay, so we know this is anode. That's why we know copper is the anode. All right. Similarly, when you look at the oxidation state for silver, it decreases. So for this reason, this process is a reduction. Okay. Remember, red cat. So we do know silver is the cathode. That's how we know. Okay. So that's why you write silver on the far right side and copper on the far left. Step 2. Working in from the left. The copper is in contact. This is in direct contact of a copper ion, okay, in the solution. So we write AQ for the solution and use the single vertical line to represent the phase boundary. And then we use a double vertical line to represent the salt bridge. The silver is also in the aqueous solution. You can specify the concentrations, if known, for the aqueous solutions. So we can use the 3-step procedure to complete the cell notation or cell diagram. Look at one more example. Write the Voltaic cell reaction and write the cell diagram or cell notation for a cell in which magnesium metal is oxidized to magnesium ion and copper ions are reduced to copper metal. So we know we have two reactions, two half reactions involved. One is magnesium and a magnesium ion, copper and a copper 2 ion. So we need to write a redox reaction and the cell diagram. From the description of the half reactions, we can identify magnesium reaction as the anode half cell because it's more reductive, and copper reaction as the cathode half cell. We can write the balanced reaction and using the steps outlined previously. So for the anode, the oxidation is what happens. You have magnesium being oxidized into magnesium ion. For the cathode, copper is gaining electrons and being reduced to copper metal. When you write the overall reaction, you add these two reactions together and the electrons will be cancelled out. So the balanced reaction is over here as the overall reaction. When you write the cell diagram, remember the anode will be written on the far left and the cathode will be written on the far right. To remember, use the phase boundaries, and also don't forget to use double vertical line to represent the salt bridge when you write the cell diagram. Since there is no concentration, we are going to just leave it as is. So let's think about it. Based on the cell conventions, we know that magnesium is being oxidized. So it is going to be the anode. it will be written on the left side of the cell diagram, and copper is being reduced at the cathode. On the right side of the cell diagram, that's where copper will be written. Magnesium ion and copper ions involved in these half reactions imply that there is a transfer of 2 electrons from the magnesium anode to the copper ions in the solution in contact with the copper cathode. So that's the whole process. So as we just learned, we can use different metals and different solutions and put together a battery. But how do we calculate the cell potential? We use the standard reduction potentials to do this calculation. A standard reduction potential provides a relative measure of the tendency of a substance in its standard state to be reduced. Remember, standard states are defined as 1.0 molar concentrations for aqueous solutions, and the 1 bar, sometimes we say it's 1 atm partial pressure for gases. The cell potential will be the reduction potential for the cathode minus the cell reduction potential for the anode. Under standard condition, when you look at the knot, this knot means it's standard states. 1 m for aqueous solution and 1 bar for gases, or 1 atm. Let's look at some real examples. In this table, you see a whole list of half reactions. In all these half reactions, they gain electrons, which means all these reactions you see over here, they are so-called reduction reactions. That's why these potentials are called reduction potentials. So on the left side of the arrow, you see the oxidants. Oxidants all sitting on the left side. On the right side of the arrow, okay, these are reductants. So reductants are sitting on the right side. When you look at the cell potentials, the more positive the cell potential, the stronger the oxidant, which is on the left side. The more negative the reduction potential, the stronger the reductants on the right side. You see? So lithium, when you look at lithium, which is sitting on the right side, this is the reductant. But lithium plus, this is the oxidant. The oxidant is being reduced by 1 electron to make a reductant, because the reduction potential is very, very negative. So lithium metal, which sits on the right side, is a very strong reductant. Conversely, fluorine, F2, has highly positive reduction potential. So F2, which is an oxidant that sits on the left side, F2 is one of the strongest oxidant available. It does make sense because fluorine is the most electronegative element in the periodic table. So it would have the greatest tendency to gain electrons. Let's look at a few applications over here. First question, which of the following is the best reducing agent? So remember, reducing agents, when you look at the table, all in this table, these are all reduction potentials that are listed, because all reactions listed in this table, they are gaining electrons. So for this reason, the reductants will be sitting on the right side. That's where the reductants will be. And the oxidants will be sitting on the left side. And the best reducing agent is the most negative reagent on the right side. So out of these three, which one is most negative? Negative 0.76 is the most negative. So zinc will be the best reducing agent. It's not zinc plus, because zinc plus actually serves as the oxidant in this reaction. So E is the correct answer, not C. We can change the question to, what if we ask, which of the following is the best oxidative agent? So, best oxidative agent, that means we look for the most positive reduction potential on the left side. So the most positive would be a 0.80, and on the left side will be the oxidants. So Ag+, this would be the best oxidant. Okay, so let's summarize everything we just learned. So this is a review here. The best reductant or reducing agent. Best reductant has most negative reduction potential. And do remember, the reagent will be sitting on the right side. And the best oxidant will have the most positive reduction potential. All oxidants will be sitting on the left side. Let's look at one more example. Predict the best reducing agent using the standard reduction potentials. In this example, we have 4 different metals listed over here. We are asked to predict which one of these is the best reducing agent. So first we'll have to find out those 4 reduction potentials. So silver, that's the first one, that has silver on the right side. Then we have copper. We also have iron. The next one is chromium. So these 4 reduction half reactions have corresponding cell potentials listed. Remember, the best reducing agent will be sitting on the right side with the most negative reduction potential. So with this list over here, that's the most negative reduction potential in the whole list. So for this reason, chromium, which is the reductant because it sits on the right side. Okay, so D is the correct answer. Let's look at one more application. Which of the following reaction is spontaneous? So we give you a series of reduction potentials over here. Which of the following reactions will be spontaneous? The first reaction, we're going to compare how the reaction is going to happen. Okay, first, this is a reductant because it's being oxidized to higher oxidation state. Okay, so this is reductant. And magnesium is the oxidant. So after the reaction, you generate magnesium, and magnesium will be the reductant. Because when you compare magnesium with the Mg2+, Mg has lower oxidation state. Fe2+ will be the oxidant. Do remember, a chemical reaction will be spontaneous if you have stronger reductant reacting with stronger oxidant, or else the reaction will be non-spontaneous. So we can compare the reductants with reductants or oxidants with oxidants. Okay, so for example, in this case, we can compare 2 reductants or 2 oxidants. Right. For example, here that's a reductant, and that's another reductant. So when you look at those 2 reduction potentials over here, magnesium is more negative than that of iron. Iron is less negative. So this means through these 2 equations, okay, we do know magnesium being more negative in the reduction potential. So magnesium is a better reductant. So this is better reductant. And this is weaker reductant. So this reaction is not spontaneous, because only when you have stronger reductant reacting with stronger oxidant, the reaction will be spontaneous, or else it will be non-spontaneous. Let's look at the second example. So we can do the same comparison. So when you look at copper, copper is right over here. Then you look at hydrogen. Hydrogen sits right over here. So when you compare the reduction potentials, hydrogen, H2, has a more negative reduction potential. And in other words, H2 is a better reductant. Again, remember, you have to compare the reductant with the reductant, or the reagent on the right side of the equation. Copper is a weaker reductant than H2. So for the same reason, the reaction will be non-spontaneous. The spontaneous reaction will always have stronger reductant reacting with stronger oxidant to generate weaker reductants and oxidants. So the second is also non-spontaneous. The first is non-spontaneous, as we talked about. The second is also non-spontaneous. Okay. Now let's look at third reaction. We can compare, and when we look at Ag, where do you see Ag? So Ag is right over here. So Ag is a reductant because it sits on the right side. Okay. Now you look at Cu. Cu is also a reductant. It sits on the right side. But do remember, when you look at this situation, plus 0.34 and plus 0.80. 0.34 is more negative than 0.80. Okay, so copper is a better reductant, but in this equation you see over here, copper is in the right side. Okay, so this reaction is non-spontaneous as well. None of these three reactions is going to be spontaneous. Let's look at some examples about the standard cell potential calculation. So when you look at the zinc and copper battery, so when you look at this under standard condition, the cathode is going to be, so look at this reaction, zinc, that's the reaction for this particular battery. Zinc is reacting with copper ion, which generates zinc ion and copper metal. Okay. In this case, the cathode is going to be the reduction. So this one is reduction because the oxidation state changes from +2 to 0. So the reduction is going to be the cathode because a red cat, remember the mnemonics? So that's why this is the cathode, okay, because that's the reduction. And for the anode, when you look at anode, this is 0 oxidation state, changes to +2. So that's oxidation because oxidation state increase. This is oxidation. Anode is where the oxidation happens. So this one is the E anode. Okay. You look this up in the reduction potential table, which will be provided in your exam. Right. So E cathode minus E anode. E cathode minus E anode. And that will give you the standard cell potential, which is 1.104 volts. Let's look at another example. This is the Zinc-Air Battery used in devices such as hearing aids. The majority of the battery volume is occupied by the anode, which consists of a paste of zinc particles in aqueous slurry of KOH. The anode reaction involves the oxidation of zinc to zinc oxide. The cathode consists of porous carbon supported by a metal screen. The air diffuses through the small holes in the battery. Oxygen from the air is reduced at the cathode to hydroxide ion. The reductive potential for the cathode is 0.401 volts. And on the anode side, zinc oxide is being reduced to zinc, and the reduction half potential is negative 1.25. So the cell or the battery potential is E cathode minus E anode. This gives you 1.65 volts. So let's do another practice. The standard cell potential for the following reaction. Okay, can you calculate this? The first thing you do need to remember, the E cell is always E cathode minus E anode. So what you need to decide is which one is cathode, which one is anode. To remember, cathode is where reduction happens, because we have red cat and N-ox. So when you do the oxidation state assignment, this is +3, and this is -1, this is +2, and this is 0. So apparently we can see iron is being reduced from +3 to +2. So this is reduction half. Or in another word, this is the cathode. Okay. And iodide being oxidized to I2 from -1 to 0. So this oxidation. In another word, this is the anode. So after we correctly identify the cathode and anode, we can look up the cell potentials in the reduction potential table and put them in this equation. Then we can do the calculation for the cell potential. So we find out in the reduction potential table, the E for the cathode is 0.771 volts, and that for the anode is 0.535 volts. So E cathode minus E anode gives us the cell potential, which is 0.236 volts. So when we look at the cell potential, because this one is a positive number, that means this reaction is actually a spontaneous reaction. If E cell is negative, the reaction will be non-spontaneous. When an electrochemical cell is operating under standard conditions, that means the aqueous solution will be 1.0 molar, and the partial pressure for all gases will be 1.0 bar or 1 atm. Temperature will be 25 degrees C. And the cell potential, it will be reported as E cell under standard condition. That's what will be reported under standard condition. The value of the cell potential gives us a measure of the driving force behind the flow of electrons. For this reason, it is sometimes called the electromotive force, or EMF. The unit for the cell potential is volts, which are equivalent to joules per coulomb. In other words, the cell voltage provides a measure of the amount of electrical work in joules that can be performed by the cell for a given transfer of electrons, because charge has the unit of coulomb. The Gibbs free energy can be calculated by this equation. The delta G for the cell is negative N times F times E cell, and N is the number of moles of electrons being transferred, and F is the Faraday constant, which is 96485 coulomb per mole of electrons, or it's roughly 9.65 times 10 raised to 4 coulomb per mole of electrons. Let's do an exercise. Calculate the value of delta G, Gibbs free energy, okay, and the work done on the circuit for the reaction listed below. Magnesium reacting with copper ion, which generates magnesium ion and copper metal. So we are given the balanced reaction, and the cell voltage E cell is 2.71 volts. We are asked to calculate the value of the delta G. To remember, delta G is, so delta G is always negative N times negative N times F times E cell. So we do know the number of electrons being transferred is 2 electrons because we look at the oxidation state. So it's from 0 to plus 2. So we do know this is oxidation. At the same time, it's 2 electrons being transferred because it's from 0 to plus 2. Okay, 2 electrons being transferred. So then we can substitute all other numbers in. It's 2 moles of electrons, that's the N, and this number could be written as 96485, okay, or roughly 96500. Right. And then the cell potential. So you put all numbers in, delta G is a negative number, which means the reaction is spontaneous because delta G is a negative value and the E cell is a positive number. Have you ever wondered how we put together the table of reduction potentials that was initially shown in the previous slides? We actually arbitrarily assign the standard hydrogen electrode reduction potential to be 0. Then we compare all other reduction potentials with standard hydrogen electrode. In this way, we can measure the other half-cell reduction potential. For example, the standard hydrogen electrode serves as the cathode in the measurement of the zinc half reduction potential, which is measured to be negative with zinc. E cell will be negative 0.762. Okay. In the other case, the standard hydrogen electrode serves as the anode, and we do the E cell calculation, and we determined that E for copper is going to be plus 0.342. That's how we measure the standard reduction potential. In 1889, a German chemist, Walter Nernst, derived an expression relating cell potentials to concentrations of reactants and products. The derivation is recreated here. This equation is called the Nernst equation after Walter Nernst. If we stipulate that temperature is 298 degrees C, then we substitute the value R equals 8.314 joule per mole per K and convert from the natural log to temp-based log. We obtain an alternative form of the Nernst equation, which is also listed here. The Nernst equation allows us to calculate the E cell as concentrations change. As the cell reaction proceeds to the right, the concentration of products increases and Q increases. As Q increases, the value of the E cell will decrease. When E cell reaches 0, the cell reaction will stop because the cell reaction has reached equilibrium and there is no cell potential. Let's work on an example. Consider the cell reaction below, starting at the standard condition, and with this equation, determine the cell potential after the reaction has proceeded enough for the zinc to have changed by 0.35 mole at 25 degrees C. So we are given the cell reaction and the standard initial conditions. We know that a cell reaction has proceeded sufficiently for the zinc to change by this much. Okay, so we are asked to calculate the E cell after the reaction has proceeded. So do remember, the standard E cell, E naught, will be E cathode minus E anode, which gives us 1.104. Right. According to Nernst equation, we need to know several other pieces of information. Based on the cell reaction, we know the number of moles of electrons transferred, N, is 2, and the Q is defined as zinc concentration over that of copper after the reaction has proceeded and zinc concentration has increased by 0.35. Remember, it has changed by this much. Under standard condition, all concentrations initially will be 1.0 molar. Since it has increased or changed by 0.35, so the final concentration for zinc will be 1.35. And the copper concentration will have decreased by a stoichiometrically equivalent amount of 0.35, so the final will be 0.65. So we can substitute these values into the Nernst equation to calculate the new E cell under the non-standard conditions. So we can do the E cell calculation. E cell is E cell naught minus 0.0592 over N, which is 2, times log Q, zinc over that of copper. So we substitute all the numbers in, and we have the new E cell 1.095 volts. Right. Let's think about it. The reaction has proceeded toward equilibrium by some known amount, so the reaction should be less spontaneous. This is consistent with the decreased value of E cell compared to E naught. Let's consider the lead-acid battery used to start car engines. The overall cell reaction is shown over here. The standard cell potential is calculated to be about 2 volts. When we use this in the car, we have 6 cells in series to achieve about 12 volts of a total voltage. As the reaction proceeds, the concentration of sulfuric acid will decrease. Then the Q in the Nernst equation will increase, and the value of the E cell would be expected to decrease. We can actually use the Nernst equation to calculate the actual change in the E cell with this lead-acid battery. The actual change in cell potential versus percent reaction is shown in this figure. As expected from the Nernst equation, you do see as time goes by, the reaction proceeds and the battery discharges, but it's not a very dramatic change until the reaction is very near completion. The gradual change of E cell is due to the logarithm relationship between the E cell and the Q. The result is for most battery, including car batteries, can deliver a voltage very close to their designed potential until they are nearly completely discharged. This is really important for the batteries to function properly. Let's now discuss the relationship between E cell and the equilibrium constant K. So at equilibrium, according to Nernst equation, E cell equals E naught minus RT over NF times the natural log of K, because Q is K at equilibrium, okay, and E cell is 0. So you will have the rearranged Nernst equation in this way. So when you redo the calculation, you have a relationship of log K equals N times G over 0.092. Or you can rewrite as E cell equals 0.0592 over N times 10 base log of K. These two equations are equivalent. Let's look at one example for the relationship between the cell potential and the equilibrium constant. Calculate the K from the standard cell potential for the reaction below. We are given the reaction. So when we are given a balanced reaction at a certain temperature and asked to calculate the value of K, From the cell reaction, we can identify the anode and cathode half reactions. From the half reactions, we can obtain the E cell under standard condition for the half reactions. Okay, so according to this equation listed over here, we can calculate the K. So the cathode is identified. This cathode is where reduction happens. Okay, this one is reduction. That's the cathode. This one is oxidation, so that's the anode. With the correct identification of the cathode and anode, we can calculate E naught. For the standard cell potential is the cathode minus the anode reduction potential, which gives us 0.314. And we substitute these numbers in this equation, then we can calculate the K, which ends up with a very large number. This does make sense because the E cell is a positive number, which means the reaction is spontaneous. So K should be greater than 1. The relationships between K and the E cell naught and delta G naught are illustrated in this table, along with the relevant equations that quantify those relationships. All three parameters can be used to indicate the spontaneity of a reaction, as well as the extent to which a reaction will proceed. For non-spontaneous reactions that favor the reactants or the reaction do not proceed very far to the right, K is small. K is smaller than 1. Okay? The E cell is actually smaller than 0, and delta G is greater than 0. For a spontaneous reaction which favors the products, K is greater than 1 and E cell is greater than 0 and delta G is negative. And if the reaction is at equilibrium or neither favoring the reactants or products, okay, then K is 1, E cell is 0, delta G is 0. So the last situation is at equilibrium. The first one favoring the reactants, that's the same as saying non-spontaneous. Second situation is spontaneous. So we have already covered the most important topics in chapter 18. For the rest of the slides, if you are interested, you can read it on your own. They will not be tested in your exams. Have a good day. Bye.